Alladi Prabhakar 6th Endowment Lecture. Today we gather here not but also to embrace the exchange of knowledge and ideas that such events inspire. Before we delve into the depths of knowledge, we would like to commence this event with some ceremonial traditions. To invoke the blessings of wisdom and enlightenment, I request everyone to rise for lighting of lamp. I would like to invite the dignitaries to come forward for lighting of lamp. As we stand in unity, let us invoke the divine presence with a moment of prayer. I request Pujita, second year Department of ECE, to present the invocation song.
महागणपतिं मनसा स्मरामि महागणपतिं मनसा स्मरामि वसिष्ठवासुदेवादिवन्दितमहागणपतिं महादेवसुतं महादेवसुतं गुरुगुहनुतं महादेवसुतं गुरुगुहनुतं मारकोटि प्रकाशं शान्तं महाकाव्यनाटकादिप्रियं मूषिकवाहनमोदकप्रियं महागणपतिं मनसा स्मरामि महागणपतिं. Thank you.
Last.
Ladies and gentlemen, it's my honor and privilege to welcome our esteemed dignitaries onto the dais. I kindly request Professor D. Ramakrishna Sir, Head Department of ECE, to please come onto the dais. I kindly request Professor P. Chandrasekhar Sir, Principal, University College of Engineering, Osmania University, to grace the dais. Ladies and gentlemen, it's my privilege and pleasure to invite our distinguished speaker, Dr. Tanveer Saida Mahmood Ma'am, to grace the dais. Moving on, now I cordially invite Professor D. Ramakrishna Sir, Head Department of ECE, to present welcome address to the gathering.
Respected Principal, University College of Engineering, Usman University, Professor Chandrasekhar Sir, today's distinguished speaker and esteemed alumni of the department, Dr. Tanveer Saida Mahmood, IBM Fellow from IBM Research and Adjunct Professor from Stanford University, USA, and Professor Ramchandram, former Vice Chancellor, Usman University, Dr. D. Vijay Kumar, President, OUCE Alumni Association, Sri Kishore Pasupuleti, President, OUEC Alumni Association, family members of Professor Alladi Prabhakar, retired professors of department, teaching and non-teaching staff, alumni, invited guests, research scholars and students of the department, greetings to all. On behalf of the department, I welcome you all for the 6th Professor Alladi Prabhakar Endowment Lecture. On this auspicious occasion, it is my honor to say a few words about late Professor Alladi Prabhakar. Professor Alladi Prabhakar obtained his BE degree with honors in electrical engineering from Madras University, MS degree in electrical engineering from the world renowned Harvard University, and PG diploma in guided missiles engineering from College of Aeronautics, UK. From 1950 to 1964, he was with Defense Science Service at IIT Pune, then joined Usmania University as professor. In 1990, UGC appointed him as Professor Emeritus at Usmania University. Thereafter, he was with Manipal Institute of Technology and MEMG international programs. Professor Alladi Prabhakar is the author of over 40 technical articles and the editor of journal IAT and the book Systems Engineering published by Usmania University. Professor Alladi Prabhakar has lectured at over 30 universities in USA, West Germany, UK, and Australia. Professor Alladi Prabhakar is a recipient of numerous awards, notably Government of Andhra Pradesh Best Teacher Award, UGC National Lecturer, and ISTE AP Chapter Lifetime Achievement Award. He is a fellow of IE Australia, a fellow of the AP Academy of Sciences, a fellow of IETE, and a fellow of IE India. Professor Alladi Prabhakar joined this department in 1964 and served Usmania University in various capacities for over 23 years as Chairperson Board of Studies, Head of the Department, Principal, and Dean Faculty of Engineering. Professor Prabhakar is a great teacher and administrator who worked tirelessly for the cause of higher education in India. In his honor, the department established Professor Alladi Prabhakar Endowment Lecture. In short, it is PAPEL in June 2010 by aiming lecture to be delivered annually to establish the education and scholarships of students of the Usmania University. So far, we have conducted 5 lectures by inviting eminent researchers across the globe. 6th lecture is scheduled today. On behalf of the department, I thank today's speaker and distinguished alumni of the department, Dr. Tanveer Saida Muhammad, for accepting our invitation in spite of our busy schedule to deliver this 6th lecture. With these few words, I would like to extend once again my welcome to everyone for the 6th Professor Alladi Prabhakar Endowment Lecture and express my gratitude to everyone who accepted the department invitation. Thank you.
Thank you, sir, for setting the stage for today's event. I kindly invite Professor P. Chandrasekhar, sir, our beloved principal, University College of Engineering, Usmania University, to address the gathering on this event.
Good evening to one and all. Dr. Tanveer Saida Mahmood, IBM Fellow, Adjunct Professor of Stanford University, and proud alumnus of ECE Department as well as University College of Engineering. Professor S. Ramchandran Sir, former Vice Chancellor, Professor Samin Fatima, former Principal, Dr. A. Krishnaya, Director CDAC, retired professors of our department, distinguished alumni, invited guests, teaching and non-teaching faculty members, my dear students. On behalf of University College of Engineering, a warm welcome to Madam for coming over here and sharing your views with our students as well as the faculty members. In fact, University College of Engineering always in the forefront for working in the cutting edge technologies. One of them is artificial intelligence. So hope our faculty members and research scholars make use of the today's lecture and to work towards challenges in the artificial intelligence. In this forum, I would like to request you as well as other alumni. University College of Engineering is always in the forefront to prepare our students to face the challenges and opportunities across the globe in different technologies, technological challenges. So I request or submit to you to work with Usmania University, in particular University College of Engineering, to share your expertise, to mentor our students in whatever the way we can do, we can extend to our college. So thank you. We look forward to hear from you. In this occasion, this is the idea incepted when Sir was there, Professor Alladi Prabhakar was there, and Professor D.V.R. Vittal was instrumental for starting this event, as well as Kumpati Narendra, Professor Kumpati Narendra was special, our permanent invitee to our PAPL, that is called Professor Alladi Prabhakar Endowment Lecture Committee. So in this occasion, my gratitude to Professor Alladi Prabhakar sir and D.V.R. Vittal sir, and thanks to Professor Kumpati S. Narendra Garu, who were instrumental for making this lecture committee and the lectures happening in our department. So it is a prestigious event, and we are all proud to continue this tradition. And my best compliments to Department of ECE for continuing this tradition. Thank you.
Thank you, sir, for your inspiring address on this occasion. Now let us move on to the main highlight of the day, the endowment lecture on neuro-inspired memories, driving next generation AI models for computer systems by Dr. Tanveer Saida Mahmood ma'am. Before we invite our distinguished speaker, it is my honor to introduce ma'am. Dr. Tanveer Saida Mahmood is an IBM Fellow and a global imaging AI leader in IBM research. As a worldwide expert in imaging, she is leading the company's future in multimodal bio-inspired AI and defining new features in Watson X series of products. Until recently, she was the chief scientist of the Medical Sieve Radiology Grand Challenge that helped launch the field of radiology AI and the IBM Watson Health Imaging business. As an IBM Fellow, she is also involved in long-term strategic thinking on the evolution of the field of AI. Ma'am graduated with a PhD from MIT Artificial Intelligence Lab in 1993. Prior to coming to IBM, she led the image indexing program at Xerox Research and was one of the early originators of the field of content-based image and video retrieval. Over the past 30 years, her research interests have been in a variety of areas relating to artificial intelligence, ranging from computer vision, image and video databases, to recent applications in medical image analysis, healthcare informatics, and clinical decision support. She has over 300 referred publications and over 170 filed patents. Dr. Saida Mahmood has chaired many international conferences over the years. She is fellow of IEEE, AIMBE, and AAIA and MICCAI societies. Please welcome ma'am with a huge round of applause.
That's good. Can people hear me okay at the back? Yeah. Thank you very much, all of you, for these great introductions. And I still feel like I'm a student coming back after a long time here back to Osmania and to engineering college. And yes, I still remember this auditorium in its earlier form when I guess I was the recipient of maybe the first cake in IR gold medal or something. So, and I did not know I was going to receive it. And I happened to just come to the department, and then they grabbed me and said, "Oh, Maya, you need to be in the auditorium because you're winning an award." So that was exciting to get the surprise over there. But always valued the education I got here in Osmania. And then as I moved on to others, I think the firm foundation laid by the subjects that we covered in signal processing and in the firm mathematical foundations really helped me a lot as I progressed through my career. So grateful for that. So, and Professor Larry Prabhakar and Professor V.U. Reddy and Professor T. Reddy were my mentors throughout my education in here, and I am deeply grateful and honored to have to present an endowment lecture in Professor Larry Prabhakar's name. May God bless his soul. So here, as you heard from my bio, I have worked in a variety of fields, and this is my latest pet project. As an IBM fellow, and you are the top scientist in the company, and you have some latitude in trying to carve out new directions and think long term. So I've been fortunate to be part of exploratory projects throughout IBM research, and these are long-term projects that we start as something called grand challenges. These are, of the upwards of $100 million initiatives that may launch new $1 billion worth of businesses. So Watson Health was one such business. And so when that was over, we thought of some new things to do. And what I'm going to talk about today is some of the latest thinking that's going to appear in this year's NeurIPS forum. So some of the work that I'll present is a bit of an advance over that. And in a topic that was near and dear to my heart, because my minor was in neuroscience back at MIT, and I always had this idea of my thesis was on attentional selection mechanism in the brain and how that can be used to quickly recognize objects in images. As you heard, my first 10 years of work after graduation was in computer vision field and so on. So when I had a chance to revisit that area, I said, why not bring back those topics of neuroscience and blend it with AI? It's not that neuroscience and AI are that far apart. Of course, the neural network field, as you know, has shown that the relevance of neuroscience already to AI. However, once the firm foundations have been laid, then people just went off in different directions, neuroscience, scientists in their own fields, and AI, and became very computationally oriented as they went. But now people are feeling the need to bring them back again and then apply them in real-world context in enterprise applications. So this is one such project in which we are trying to take inspirations from the brain and then try to apply that to build next generation foundational models in artificial intelligence. And so to give you a flavor of that as we go. How do we switch? Is there a way to advance the slides? Okay. If you have a clicker, that will be good. Oh, there it is. Operated. Okay, so we'll start with this exercise to see how the brain remembers things. Okay, so I'll flash this to you. First, looking at this. Maybe anyone saw that picture? What did you observe? Motorbikes? Kids? People on motorbikes? Yes? How many do you think there were? A lot, right? But there were a few that were noticeable up in front. How many do you think? A couple. Okay? So if you were observant and you saw that, and obviously I didn't give you the cue ahead, so you wouldn't focus automatically on it, but that's where the brain's mechanism, the attention mechanism comes in. So when you look at this, one of the things that happens is the brain forms salient representations of the underlying scene, and things pop out automatically, even though you're not asked to look for something. But once you're asked to look for something, now you will notice things that you didn't notice before. And so the brain's attention mechanism operates in two modes: the attract attention mode, in which you let things in the scene attract your attention naturally, and that's why that first exercise that I showed you, and you still got the gist of it. And then the next is, if you pay attention in here, you can now answer questions about a language perspective. And then you need to now remember and try this back to what you've already seen as identities of objects, and put them in your memories, which are the semantic memory and the episodic memory. And we'll talk more about this as we go. And so these are essentially forming representations in the brain for each of the concepts that you are looking at, and each of these colored regions may be different types of concepts: visual concepts, language concepts, as we go. So, and then once you have that, you now have somebody ask the question. Like, if I wanted to know what was the color of whether the rider was wearing a blue helmet, that's a very specific query. So now you are able to take the query's information, do another level of sensory processing for the query. In this particular case, it was an audio query or a visual query by asking, show me this, or it was just a language query. You would do the necessary processing, pay attention to what was asked, which in this particular case was a blue helmet, and then to be able to use your recall mechanism to push those out. Okay, so that's how the brain is processing information, and that's how the memory in the system in the brain is helping coordinate the learning that is going on. But there is a circularity there, because to learn, to memorize, you also need to learn. And once you learn, you do memorization, but once you memorize, you can also apply it to learning for other tasks later. So memories are basically the faculty of mind that encodes, stores, and retrieves information. So there are three processes: ingest, store, and retrieve information. If you look at that, isn't that how the computer memories work? They also ingest, store, and retrieve. So it becomes a natural thing for us to think about, maybe there is a parallel between these two, and we can actually use the human brain's memory system as a model for building our computers' memories as in future. So the neuro-inspired memories is really about making a computational model of computer systems built on a computational model of human memory. Now, you may ask, why do we need them? I mean, why do we need such a model? And is it really necessary? So here I give you a couple of examples, maybe, and dive a bit deeper into, to tell you that this is the next thing as we talk about, because the best way to design artificial intelligence systems going forward is to think a lot about how the brain is doing, because in these tasks that the brain does well, AI is not doing as well. But in the tasks that the brain probably doesn't do well, AI is doing pretty well. So when we talk about these, the first example I'll give is in terms of generation of actual memory storage systems that are going to come out. You might see some announcements already by IBM, but there are also other companies putting out something called CAST, or Content-Aware Storage Technologies, and then an application of it in healthcare as well. So let's go through that. And if you look at that, it's now going to be permeating devices, data centers, object stores, lake houses. So no matter where you go, where there is storage happening, there's going to be some smart storage systems coming up that are aware of the content that they are housing as such. So essentially, the generation of storage systems has gone through blocks. So some of us who have studied computer system architectures and the use of storage systems as way of CPU plus, the von Neumann model, for example, people have studied that in computer architecture. So we've played with some of these storage devices over the years, from hard disk drives to block storage to file storage to object storage, which is what everybody nowadays uses in cloud object stores. But But the mechanism and what is the perception of storage is very passive. It is a supplier of data, and all the intelligence and the application lies in the application and happens in the cloud as such. So what we are trying to do is change that and essentially bring some intelligence down into the storage systems so that the storage systems understand what it is that they're storing. So if you do that, you might now be able to answer questions like this. If you wanted to know, is there, in the data that I've just gathered, is there any personal information? Is there a possibility of a data leak? If you want to ask that question to a storage system right now, what can you do? You can only ask for some specific files by their names. That is the current technology. Even if you go to S3, Amazon S3 object stores, you have to give the URL. But there is no way to natural language query them and let the machine understand what it is that you're asking. If you want to now serve not just an entire video, but just a section of interest, such as, oh, get me the video that talks about a running faucet, then you need to understand what is a running faucet, in which video is actually a faucet being shown, and when is it considered running. So you should be able to hear the sound of it running and be able to take those out. Thank you. So this is one such simulator we built where you have some incoming content and you have a number of file systems storing videos, and you basically ask that question. And so you can see a lot of these, and we are looking for videos of running faucet. Which ones do you think is the right one? As they're all playing. Some of these should be playing. So there's a faucet here. People can recognize that, right? And then there's another faucet here. But between these two, which is the right match? Because one of them is leaking. The others are not. So maybe just fast forward these. I'll play these. OK. So in order to understand that, you need to know that these are the images that are right, because there is actually a tap or a faucet, and current computer vision systems can name faucets, so you can detect those. And then you can do audio foundational models that can recognize lots of different sounds, so you can understand a sound of water drops. And so if there is a leaky thing, there should be a sound of water drops. Now, I may not be able to play the audio because I think my machine's thing is tied to my earpods. So maybe it's going over there. But otherwise, you would hear the sound of water dropping in here. OK. But in order to say that, if it is a leaky faucet, you have to understand a leaky faucet is actually a concept called faucet, and an operation can leaking, and tie the two together. So this is a semantic level understanding of your query. And to do that, what you have observed from episodic memory, which is the content you've just seen, in order to answer the question that is being asked, you have to also consult your semantic memory, which is the memory of facts and events that are declarative, something that are non-autobiographical, so that you understand what is a leak concept, or what is a faucet itself, and then the two coming together. So this is where the semantic memory comes in. And that's what is used to recall. And now you will actually play, when you play this video, it has automatically indexed it into the section of which is where the leak is showing, if you've seen the drop of water over there. Sometimes the light here is probably not the best place to see this. Anyway, so this is one such example where in next generation computer systems, and if you go to Amazon S3 store, you can now ask for natural language-based query and get the content that you want, and then start from a higher level of plane. So those who are working in AI know, worked with Keras, TensorFlow, yes? So they have made it easy for you to play with the underlying architectures. So that's the level, a layer of abstraction that has helped you program. So that'll be the case with storage systems, that they will already retrieve the right data for you so you can build your models quickly. OK, moving on, the second example I'll give is in the context of memory impairment. Obviously, since my interest was in healthcare, I'm also looking at its application in in healthcare, and particularly in dementias, excuse me, where you have memory losses, and some of them are irreversible losses. And I know a lot of people are working on different types of cures, but their quality of life is pretty bad. And some of you may have elders experiencing this already. And in America, there are people who call the police on their children because they cannot recognize that's their child. So if we can cure, while the scientists in different disciplines are looking after cures for such diseases, we were looking at ways of giving them memory prosthetics. These are artificial memories that you can now give to patients who essentially use these sensory systems like cameras and auditory devices to listen and grab everything that goes on in the scene, understand, and convey it in a subliminal way to the patient so that the patient is aware of what is going on as such. So you can see some scenarios like these where your daughter Anne, so in order to be able to recognize that this is your daughter, this is something that the machine has to first recognize itself, that it is the daughter, and then be able to convey that back to the patient in a way that is not, that's not scary to the patient as such. So this obviously, with the current technologies, we are able to segment the scene and look at different objects in the scene, but we also be able to identify their changes in appearance every day. So this lady who is attending to him comes with dressed differently each day, sometimes with glasses, sometimes without. So to be able to do person identification in various settings and to understand the relationship with the patient also is something that is a new work that is happening as we go. Okay, so you saw these two very disparate applications, but both can be served by a common AI system, because the underlying technology is similar. So if you want to build a self-aware system, it should possess some properties, such as ingesting any incoming content, encoding them, organizing them, recalling them, and to be able to do that on the fly, updates as new information comes in, to tie it back to old information, and to be able to adapt to new queries as it comes through. So you can ask, what is such a system that would actually do this in a very general way? And you can look around in current AI systems. There's nothing that meets this sort of criteria. And so where do we look back? We look back in our own brain systems and then try to develop a computational model so that we can apply that to these use cases as we go. So here's a little bit of neuroscience intro for those who don't have the necessary, but if there are any clinicians or neuroscientists in the audience? Yes? Okay. So the kind of memory we are talking about is explicit memory or declarative memory. There's also other types of memory systems in the brain, like skill memory, how to ride a bike. So that's a motor systems also involved. But when you have declarative memory, it's mostly about facts and events, and it has subsystems. So when you talk about, and here's just the breakdown of the different kinds of memories. And what is involved in memory is the hippocampal system. This was a discovery that was done with the Henry Mason time as a patient who had epileptic seizures, who was operated upon, and as a result, he ended up having memory losses. So this is the hippocampal system, and this was a landmark paper from one of our colleagues at Stanford. In fact, he's one of our collaborators. Back in 1995, he discovered that memory is distributed in the brain, and the hippocampal system is simply the gating mechanism to process the incoming information, analyze it, index it, and then the storage of memories goes back into the various sensory areas where they came from. So the visual memory will go back to the visual areas, the auditory memory to the auditory areas, and so on. So you can see over here the different areas and the current way the attention system is controlling the flow of all of these as we go. I want to make sure I'm not It's too slow in my pace. Okay, so basically, we came up with this idea that if we could model the declarative memory system in the brain and look at the role of attention in forming these representations, perhaps we can come up with an explanation, even in machines, on how to implement such things in computer memories. So if you look at the neural basis of memory, there are 4 major subsystems involved. There is the sensory subsystem, which you saw in the video examples, and also the motorbike example. There was the visual system that was coming into action, but in general, it could be other sensory systems as well. Then there is the hippocampal indexing system. And so the indexing process means organizing the information, correlating to what you know, and storing it in such a way that you are able to do a recall. The neocortex is the area where the memories are actually going and staying as such. So the semantic memory stays closer to the language area, and the episodic memory goes closer to other parts of the brain where there is respective types of memories, so visual memory closer to the vision system, and so on. And then the attention system controls the operations of all of these. Now, if you look at the sensory system, there are different pathways. I mentioned the visual pathway, which leads into the visual cortex. There's also the language pathway, which is in the temporal lobe. And interestingly, the hippocampal region is closer to the temporal lobe. And so you can see a dominance of language in the memorization aspects of it. For those who do religious texts and all, they memorize. That's rote learning. And there's a tight correlation in terms of, that's one of the forms of learning where you have both input and output devices, because you can hear and you can speak. But in vision, there is no output device. You only absorb information, but you cannot relay back as a screen. Like, there's no display that comes out from your brain to show others what you're seeing. However, so the way you do it is by description. When people ask you, and you can get down to finer and finer details, but it's only an abstraction of the scene. So to what extent does the brain encode this information, and how does it do it so that you can actually convey this back to any level of detail? But at some point, you blank out and say, oh, I don't remember. Like this example I gave about how many people in the motorcycle image. I don't think you remember. You can take a guess, but you won't, because you didn't notice it at the time of coming in. So that didn't go into your long-term storage enough to be able to recall. But do you remember those 2 motorcycle riders? Probably yes, right? You just saw them anyway. But there's also the saliency aspect that highlighted them, so you remember them better. So that's how the brain is doing the selection of selective processing of information, even in representation as such. To utilize that, the main indexing mechanism, which is where this processing happens, has 2 major subsystems. One is the trisynaptic circuit, which is where the information circulates in a circuit form. For those in signal processing, you understand the circuits concept over here. And there is also the entorhinal cortex, which is like a gateway of information in the sense that visual and language integrate. And you then localize objects in space and time, and what was said at some point to who, that correlation happens in the entorhinal cortex, and that regurgitation of that information in order to remember happens in the trisynaptic circuit. And then I already mentioned that once you do this memory consolidation for autobiographical memories, which means the memories of your own experiences, like what I'm giving as a lecture here is something that you will remember as part of your episodic memory system. But the concepts you learn from my lecture in terms of what is episodic, what is semantic memory, and the abstract representations of information, or the concept of a leaky faucet that you heard, goes back into your semantic memory as concepts you have learned from the point of view of learning as well. So now, underneath these systems are subsystems that are helping them do their job. So the entorhinal cortex gets information from 2 pathways. One that is trying to localize an object, and one that is trying to identify the object, which is very interesting that when you recognize an object in an image like this, you are doing both. You know where the object is, like I'm standing in this section of the dais or podium, and who is standing here as well, the identity. And they happen to be two different subsystems. So the perihynal cortex does the identification of objects, and the parahippocampal cortex localizes the objects. And these two subsystems feed into the entorhinal cortex to merge and fuse the information so you can actually do this analysis. So these are some flows, information flows drawn for for ease of explanation, but the real model looks like this. So this is the computational model we developed to explain the various phenomena of how the attention subsystem modulates the control and how you can see different subsystems going. So I've already explained some of these systems as we go, and what we'll spend in the rest of the lecture is saying, how did we implement each of these? The entorhinal cortex, what goes on, what are the cells in the entorhinal cortex, and if you emulate them, what can we remember? How does the semantic memory get formed? And how is knowledge represented in neural embeddings? And can we develop a model of that? Then we have episodic memory. Can we remember facts? What is the representation the brain is using? And how are the episodic memory elements tied to the semantic memory elements so that you absorb the information in the right context as you do? And finally, in the trisynaptic circuit, how does the indexing mechanism and storage happen and the representation creation, which allows you to, in an implicit way, represent. Most of us are familiar with search systems, Google search, or you go through any other models with generative AIs, like in RAG applications, you do search as well. So the traditional notion of search is you're able to ask a query and then go and physically search through your indexes to locate the object. But the brain does not do that in terms of physically going through this. It is immediately able to answer some of these queries, and some of this comes from the ability of the brain to reconstruct the things. So if we were to look at that paradigm, we might lead to new ways of searching as we go as well. And I'll show this by an example, and this is one of the works that's appearing in NeurIPS this year. And so, I mean, maybe we won't spend too much time on this, but there is a difference in the way we are trying to implement this in memory systems, different from traditional database systems, from search and retrieval systems that happen in general search engines. And it's also different from the content-based retrieval systems we did years ago when I started that field, along with a number of researchers. And that was about how to be able to partially remember content and to be able to recreate content. So some of these things are coming together to explain this process at a much higher depth. So what we do in IBM research, and this also spans my tenure at Stanford, where I work with students to explore different aspects. The healthcare aspects are being explored with the students at Stanford, and then the computer system aspects come at IBM research as well. So many of the topics we'll talk about today is about ingest, store, and retrieve operations and the new neuronal models that are emerging. And the highlighted sections are what we are actually doing in implementation. Now, when you see the description, it might feel like, hey, that's like another AI model. And yes, the answer is yes. Eventually, you need to build an AI model to actually execute certain things. But it's the design principle of it, the philosophy behind how we do this, and that also translates into the operations you do differently. But the end functionality might look like some other search engine that you may have seen. So let's start first with the semantic memory, because that's the easiest to cover and things that you can easily relate to as semantic memory. So most people are familiar with the term foundational models, yes? And what did the foundational models theory saying? That it's possible to build one model with lots of data as input and serve many different use cases, right? But that comes from data, so it's a data-driven approach. But the brain is actually the opposite, in the sense that it is knowledge-driven as well, and in the semantic memory context, I'm saying. And so if we can think of a foundational model for knowledge, where you can take different knowledge subsystems that are already out there that have described ontologies and knowledge graphs, and bring them into memory and make neural embeddings of those. Most of the approaches that have gone through representing knowledge have been taking explicit representations like knowledge graphs, and they do graph-based reasoning. And this leads to complexity because doing graph searches, as you know, can have NP hardness in some areas, NP completeness in others. So getting those type of systems to work at scale is going to be hard. So on the other hand, doing things that are neural embeddings would make it, with the current vector database technology, people have already adopted those. So, but that technology exists for data. How can we do that similarly for knowledge? And by doing so, we are in one way modeling the semantic memory. So the approach we took was we need to take an ontological representation. So here I'm showing a small graph, which is in the form of a tree, an ontology. And you can see that the concepts B and C are nearer to A than the concepts G and I, right? They are further away from A. So from a semantic nearness point of view, they should be farther. In the current way of modeling through word-to-vec encoding or transformer models, you cannot ensure that if you've got 2 points, when you project them as embeddings, if they are close by, it is not a guarantee that they're actually related concepts, and vice versa. 2 very related concepts, like 2 synonyms, may be quite far apart. And that is because the data-driven approach did not take across-data correlations of the type that is explicitly defined in knowledge. So if we could capture that in an embedding space in which we naturally ensure that 2 nodes, if they're close together, they must be related. And conversely, if they're not related, they should not be close together. So how can we design an embedding that actually achieves this? So we have some starting points. We have, first of all, the knowledge. So WordNet is one such example. If you haven't heard of WordNet, it's one of the largest databases for your capturing English concepts, nouns, adjectives, adverbs, verbs, relationships. It defines the concepts from the English language. So for example, if you go to basket, you will find a synonym in WordNet, which is called hand basket, because hand baskets and baskets are related. But if you go and try this approach and learn an embedding that tries to traverse it in this semantic space, you can get a lot more related concepts. Not only hand basket, but also creel, frail, bread basket. Some of these terms you may not even have heard of, but that's in English language, all have, in one context, the meaning of a basket. But if you just take the word basket, it has many different senses. What do you mean basket? Hand basket as a hamper? Or basket as in basketball, throwing a basket. And when you heard the word capsule, what do you think of capsules? Pills, medicine? But there's space capsule, there's a time capsule, there's also a writing capsule, right? When you write a nice piece of text, that's a capsule. So the word capsule has many different senses. And this is one lesson for you. From a transformer model perspective, people haven't captured the senses explicitly. They capture it implicitly by use. So if you have it in a use context, it occurs in a specific way, they know that that has a different meaning. And that's all there was to transformers when they said every word may have a different encoding in a different sentence. And the reason for that is essentially an implicit way of modeling senses. But when you model knowledge, you can explicitly model senses. Because in WordNet, you can now have formal notations to model senses and bring those things together. Anyway, so we designed using, I don't know how many people are familiar with supervised contrastive learning. This was a paper that appeared in NeurIPS 2020. But it is an approach in which you can have labels for the data. So in this particular case, the labels are, these things are synonyms. So knowing those, you can actually construct new kind of neural networks, which not just do a point in multidimensional space, but actually part. Okay, got it, thank you. Yeah, so you can see that the space is partitioned into islands, and each island is a new concept, and all the concepts related to it. Notice that some islands are bigger than others. Why? Because capsule has 9 different senses, so it's going to have, in each of these 9 different meanings and synonyms. But some words mean just one thing, so there's not a whole lot of synonyms associated with them. So, and that's how it should be. But in current ways of modeling, in transformer models, it's just a point in multidimensional space. So we are saying that a new way of doing embedding is through islands, where you can bring different sizes based on the semantics of that concept and build it automatically using supervised contrastive learning, where you're using the sigmoidal loss function and use the things that belong together, in this particular case, two synonyms of the same word versus everything that is not a synonym as a negative example. So use contrastive learning methods where you pull apart the parts that are supposed to be synonyms close to each other and push away those that are not close to each other. And by design, your embedding will now have a feature that those that are nearby are already related concepts. And so this is one technique we actually implemented. We did several comparison studies with different methods of knowledge representation, and it is beating the state of the art. And interestingly, this is also a concept that now got picked up by a product. So if you saw for Cloud Pak for Data in IBM, and semantic search, and also for watsonx.bi as a cognitive assistant for business intelligence products, they take natural language queries which have this side of semantic understanding now built in. So this is one example where, starting from semantic memory as a concept, we built a neural embedding which actually implied it for certain ontologies, so WordNet and finance, but you could carry that over to different and make a foundational model out of knowledge and be able to now relate two concepts very clearly through similar technologies like in vector databases, except now the difference is what is the embedding that you store in such vector databases. Okay, so this is one such example. Let's go to the next one. Now we'll get to a little bit more looking deeper into the hippocampus. As I mentioned, hippocampus is an area which has the trisynaptic circuit. So the circuit, this is the circuit we're talking about. Information, as you can see from the entorhinal cortex, enters. The first stop is the dentate ginal cells. They are granular cells. They're connecting to a region in the brain here, which is the CA3 region, through some mossy fibers. And you will think, but why mossy fibers? What good are those? And what function are they doing? What are the cells in these areas? So the CA3 pyramidal cells, then on to the CA1 pyramidal cells, where there is a sense, a representation of space and time. Interestingly, over here there are cells that each cell can localize a point in space. And when you integrate, you can do a space and time. So imagine that. People have heard of the grandmother cell theory, that there is one cell for each face. So something like that here happens in the hippocampus as well. That was more in the visual cortex area. And the reason why it's a circuit is information comes from entorhinal cortex, goes through this pathway, and then goes back out through the entorhinal cortex into the various sensory systems in the brain. But if you look at the cells, some of these cells have some very interesting properties. So one of the cells we'll focus on are in this region of the brain, where you have recurrence going on to learn as a recurrent form of learning. And for those who have watched this year's Nobel Prize, one of this was on Hopfield networks, yes? So Hopfield, John Hopfield, whose student is Dima Kroto, another colleague of mine at IBM, and we work in this concept, and some of the work I'm presenting now comes from that origin as such. So we'll look at one of these cells, and there's a lot to talk about each of these cells, but I'm not going to have time to devote there. But so let's look at the idea that came through looking at the cells in the hippocampus. They are forming spin circuits. So John Hopfield was a physicist, and he noticed this like a spinning electrons concept. He saw a parallel that's going on in the brain, and he tried to model that from looking at the Hebbian learning mechanism that happens in the brain. But essentially what it is doing is energy minimization. So it thinks of when the state of the system, if you think of a recurrent network, it's a dynamical system. And some of you in signal processing know very well what that is. And when you have that, you have state spaces defined. And these state spaces form these energy landscapes. And when you are trying to remember things, what happens is each of the state of the network, there are some valleys you reach there, and that's where the memory is stored. So basically, from a Hopfield theory, memory happens by energy minimization process. Notice that this is not the search process we are talking about as an explicit search mechanism, but in some sense an implicit search mechanism. It is something that's already something you're doing in your numerical optimization, in your neural networks, when you do backpropagation, right? And you do your optimizations. So this is something like that in here, but there is a special kind of optimization we do here to bring them into these landscapes. And that's how you recognize a pattern. Any pattern that you can store happens to be within this energy minimization landscape. So this theory was known for a long time, and that's why it was called the dense associative memories. And what we mean by associative memories is you need to give a piece of the memory in order to recall the rest. So if you are given an image like this, if you're given an image like this, only half of the image is shown, and then given these images, it knows that this pattern matches this the best, right? And therefore, it spits out that as the output pattern. Now, what do you mean by spit out? By spit out, I mean the energy minimization happens, and all these cells evoke a response, and then the ultimate emergent response is this. So in some sense, the search is done implicitly by the cells settling down into this steady state as such. So this can be seen as a memory, but look at, can you think of some drawbacks for this type of approach? The most talked about drawback that everybody has is these memories can store only a limited amount of information. So they're not very scalable. Because after you get a lot of concepts to store, they tend to get confused. As it happens in any local minima, when you have energy landscapes that are common, you land in local minima. So something like that could happen. But to me, the biggest disadvantage was, hey, I'm in a storage system. I'm asking you a query. I don't have the image to give you. Half of my query should be matching what's there in your image. I cannot guarantee that. So we have to remove the requirement that if it is associative, it cannot be the same queue as your content you're storing. So if you are having an image, you may be able to give language query, and you should still be able to recover. Now imagine the concept. You are given these images, you're processing something in your Hopfield network, and you're getting rid of these, because now it's a neural network. So the information about your images has gotten into a network. And then you're giving a piece of the image, one of the images that you're trying to recover, and get this back. So we are going to show you the new results that's appearing this year, where we take care of two of the limitations of Hopfield networks. The first limitation was the metastable state. The fact that as the number of things you want to store grows, you are going to get muddled, and the information is not going to be uniquely recovered. And we'll show you examples of that. And then the second part, which is you don't need to give content to get content. You can give natural language queries. You can give some other associations that are much easier for you to obtain in a search setting and still be able to recover content. OK, so let's go there quickly. So the idea of the neural network, the recurrent neural network, is, as we've shown over here, every neuron gets its output going back to every other neuron except itself. That's the recurrence connection. And this leads to Hebbian learning, which essentially means you are computing from the stored memories to the query a similarity function, which we showed in this particular case. And then you do a softmax operation, and then projection, and then so there is some coefficients that you also optimize, the weight functions. So the basic steady state equation, as you can see over here, is modeled like this. Okay, so the drawbacks, as I said, is, so suppose you have these images. When you are given a retrieval queues, like half of these, as you grow the number of images, they end up in metastable states. Only one of them got recovered correctly. The rest are something jumbled. Okay? So first, let's see how we address the metastable problem. So here's an idea that came saying the reason why we are having metastability is because the input pattern, you're storing raw images, which have an intensity distribution all over the place. If you could simplify those distributions and instead encode them, then the encoded representations may be a better way to separate the patterns. That's the idea. Now, how did that idea come about? By looking at the trisynaptic circuit. In the trisynaptic circuit, you have the dentate gyrus encoding information before it got to the CA3 cells, which is where you try to do the recurrence for memorization. So we said, what if we do the encoding first before we feed to this? And so that's what this led to, a network. So here you can see, you take an image, you encode it, and then put this in the memory bank. And then, so if you do that, now you give the same retrieval cues. We start with this approach of just giving half the image, and you recover them perfectly back. This is with this encoding. Now you may ask, oh, what encoding is this? Is it true for any encoding or just one particular encoding? What do you think? Do you think it'll work for any encoding? If the principle is the same, or is there needs to be some properties met by those encodings? Yeah? What should be the property, you think? Yes, so one question, as I said, one hint I gave is that the patterns should be separable in this encoding, right? So if you can design an encoding that separates these patterns well, which means those that are self-similar are very different from those that are dissimilar, you'll have a property. Here again, contrastive learning comes in mind. Okay, so we want to be able to use this principle, and so we studied different encoders. So you can see, without encoding, the self versus non-self similarities are very muddled. They're overlapping distributions. And then as you go to diffusion models, they tend to separate out a bit. People are using diffusion models for generative AI, for generating images, yeah. And then different coefficients. But if you go to discrete variational autoencoders, some of you have learned that in your signal processing course, you can see that these are very peaky distributions. So this lets you do the separation well, and it is these that have given the best performance so far. Even though the diffusion models are later technology, but it's this property of separation that brings. So we did several experiments with different encoder strategies, and you can see over here, typically reconstruction errors are measured through SSIM, the self-similarity metrics, also coming from the signal processing world. The SSIM metric is very well used in AI community, but it has its origins, and by, I think one of the Indian scientists also did this work. We used to read his papers in signal processing, maybe. I have to remember now the name. But anyway, so you can see, and then the mean square error for reconstruction, where you can see perfect reconstructions. But if you go through just the image representation, they tend to stay high. But any of these encodings, they fall off, and the reconstruction error becomes low. So here's an interesting exhibit of 100 images that we take. I'm going to run this video, and you can see how the memory is evoked by giving partial cues in the encoded representations versus non-encoded representations. So let's start from here. You see, in a few iterations, the entire set of 100 images got almost accurately reconstructed, whereas if you just gave the raw image representation, look at the number of metastable state images. So this proved that having encoded representations is a good thing, which is, again, coming from the philosophy of how the brain does the encoding before it gets into storage. Now, you might say that that seems like a perfect reconstruction, but if you look at it closely, it is not. And that is, again, an open problem currently in this field, is how to ensure perfect reconstruction. For those in signal processing, this should be a field day for you, is, if you've done with signal reconstruction problems, coming up with good reconstruction mechanisms that guarantee uniqueness. So identity-wise, they are unique. So it's the same image, but it's not as good a quality. So if you want to have good quality as well, you need further improvement on this technology. But we got it to the identity part problem solved. Okay, the next situation was, well, I don't want to give something to get something. So what can I give instead of your image because I don't have it. Otherwise, I wouldn't be asking for it, right? So what can I give that would give us a way? So here's again, we caught an idea that the brain is doing unique associations in the entorhinal cortex. It's bringing the language cue and the vision cues together. If that pairing is unique, then it really shouldn't matter what is that association you're doing. So while most theory in half-field networks about content association or associative memories was talking about self-association between the same cues, there's also theories about cross-associations with cross modalities. So if we could bring those into bear and start from a different modality like text and encode text and then attach it to your content. So now you do an encoding of image. You take a text cue that is uniquely associated with this image, combine the two, and put it in your bank as your encoded representation. Then given a query text, which is again in a medium that you're familiar with, you now do a partial encoding because you don't know what's in here. You take the partial encoding, run it through your modern half-field network, and what you get is a full reconstructed embeddings from which you can now recover the image back. So it's like you give nothing to get something, in this case, where you're giving a text image and get back an image as that. And this also works beautifully regarding what text patterns can we use. The key is that it has to be uniquely associative with the image, but it really doesn't matter. So we tried text patterns in which we took the file name, because the file name is unique for your image. If you're trying to retrieve an image of a file, file of an image, then you would be able to uniquely encode that. So we took the file name and then turned it into an image. So this is the encoded file name, turned into an image of this background, and just given this as an input, you are able to fully recover the images back as well. So this works with any pixelized token representation brought in this form. So this said that as long as you make your association unique and bring it into the same modality, meaning both of them are image inputs, you are able to recover. The next example we said is, what if that's not an image input? I want to keep it in text form, because that's what the brain is doing, is keeping the language in language form and image in image form. It's not converting language to an image, so what if we can do that? So we bring this, and so we did this. We use now a query which is just text-only form as such. Again, you can see after it goes through these iterative steps, it settles in and uniquely recovers both of these. So this is going to be maybe the next way of doing search. I hope you guys realize the implications of this. All we are saying is, in future, when you get lots of files, like image files, you can process them through half-field networks, put them in neural networks, and throw away the files. And so imagine now the entire storage got compressed into your neural network. And then given a text query, you can evoke the file back from a reconstruction process. So this would be one of the next generation ways. I mean, the technology is not fully baked yet, but it's at least in paper form out there now. The last experiment we did is, what if the association is not unique? What if you got a language cue that was ambiguous? What would that lead to a metastable state? What would be your answer? Do you think it will recover fully again or get confused? Yeah? Take a guess. Okay, I'll give you the answer. It'll get confused because we don't know which of the two patterns are you referring to. So here's an example. The same text pattern was associated with two different images. When you now gave them back again as the cue, look at the recovery. Do you think that's perfect? In fact, it's the cross between the C and some content in here. So there are many more fishes or whatever those objects are than was there in the original image. Same thing over here. You might end up having some dominance of one image over the other, but we would still call it as incorrect retrieval. So that also tells us now that not only should your cross cue can be different, but it still has to be uniquely associated with these. Okay, so how are we doing on time? 5:42. Okay. I have one more section, maybe a shorter section, and then we can end and leave time for some questions. So now we talk about, since we've done semantic memory and we've seen how these representations are, we can now look into long-term storage of these things. And what happens in the brain is the most popular theory is the M-gram theory. And the M-gram theory is saying that memory is done as an interconnection between networks. It's the state of that network that is called a memory in some sense. And so a number of neurons are participating in different regions of the brain, the neocortex, the entorhinal cortex, the trisynaptic circuit, as I said, and there is information regurgitation happening between them in order to consolidate the memory. So we said if that is how the episodic memories are represented, what is the relation between episodic memory and semantic memory? Do you need semantic memory in order to do a good job of representing facts and events? The answer, that's how the brain is doing it, so we wanted to go and explore what is the embedding spaces on which we can base our episodic memory models so that you achieve those purposes. So at a very simple approximation, an episodic memory can be seen as a vision language model, right, as an instant, or any X language model, audio language, those kind of models. So these multimodal models have come up, and people use them all the time, like Llama 3.2, GPT-4o. All of these do cross associations and are able to store long-term visual concepts and their associated textual concepts. So you can see them as basically forming a representation here, where you have a visual concept associated with a textual concept, and that's how you remember some object. When you have seen an object, you have a name associated with it. But that name is actually coming from semantic memory because the concept is already defined in there. So most people don't think of it that way and try to model it just as, oh, I've got a language queue and I've got a vision queue, and I'm just forming a multidimensional space of two different modalities. But once you bring them into this joint space, they're indistinguishable from each other because they're both 512 length vectors, and mostly in CLIP, but once you are in the joint embedding space. So that's what CLIP was doing, was taking and text, a language queue, encoding it with language like transformer models, and then using a projection layer to project it, and then take an image encoder, similarly use whatever is respectively good, like a ResNet 101, say, and then bring them into a different projection layer. Both of these are simple multi-layer perceptrons. And then you explore self-similarity. So if there is a language queue associated with that image, like in this particular image, you say hamper. When you do a caption description, you say hamper. What else? Fruits, pears, apples, etc. So those things get associated with that image in a diagonal way, as it happens. That's what CLIP and all the current vision language models are doing. But it turns out that if you do that, two things like orbital module, space capsule, spacecraft, spaceship, they are all related concepts. But if you look at the similarities, they are nowhere, from a CLIP scores perspective, you can't really tell the difference. But from a language score perspective, they're all pretty low. So they're supposed to be high, but they're not. And look at these descriptions. These descriptions are supposed to be very close to each other, but there's a subtle difference. If you read them, you will be able to follow them a bit. But the bottom line is things that are similar, like if you think about hamper and basket, you know both of them are similar concept, but if you use such models in current retrieval systems, you're going to get very different matches. So that means there is a stability of retrieval problem with these systems because they don't have an understanding of the semantics. And that happens when you don't correlate semantic memory with episodic memory. You will be able to get such instability in results. And that will happen whether you have single words or multi-word phrases. You'll have some overlaps, but they're not identical. So what we were trying to do was build an episodic memory that is ground up using semantic memory as the underlying representation of the concepts so that we don't have this problem. So this is one of the latest works from the ICLR setting. So you can see over here how the visual concepts are associated with knowledge concepts. But while I show this in a graph form, each of them is a neural embedding that is stored as such. So this is the transformation we compute, basically an alignment transform. The actual network makes use of, so if you had two different language concepts and their associated imagery, and these are synonyms, so all A, B, and C are related concepts. What you want is a type of embedding in which you bring all A, B, and C close together, and then their associated images should go close together as well, and be separated from concept D, which is not related to it. So the way we do that is first take the semantic memory and project these concepts into semantic memory, which gives us this basis already. They're already close together by design. Then apply a transformation from this space to this space in such a way that the images also fall close together. So the end result looks like this, where you have similar concepts are associated with similar images nearby as such. And this gives rise to a much more coherent representation. So that's the latest work in linking episodic memory. This is the new neural architecture. We use CLIP as the front end to get the base representations and design an alignment transform to transform text to the semantic memory representation, which is the supervised contrastive learning method I mentioned earlier on in the talk. And then induce the transformation on images to apply the same transformation, that is the nearest text model, to align with the nearest text concept in the semantic memory space. So this is a new neural network architecture called the episodic memory. So we've done some comparison studies with overlaps. So you can see that the ratio of overlaps between images that you're coming back for the same query and its synonym is much higher with our model in compared to all the current CLIP variants. If people have played with CLIP models, CLIP-G is the latest out there. One is a very large vision language model, but there are many other variants available from Microsoft, from OpenAI, and so on. But the overall performance across multiple data sets. Now, once you are able to do good semantics, it turns out that you can also use that for good retrieval as well. Because if you are able to relate two concepts together, you can bring back more matches. So that'll increase your recall. And if you want to discriminate better and you want to separate the ones that are not close together, which is come by design in the semantic memory, then you expect to have higher precision too. And that's sort of what we observed in doing text-to-image retrieval and image-to-text retrieval results. And you can see through NDCG, normalized discounted cumulative gain, as one of the metrics, which has bundled in it both precision and recall, and mean average precision, which are popular measures for search. So you can see that it beats state-of-the-art quite a bit by the use of these memories. Okay, I think I'm going to stop the next section and maybe jump to the conclusion, given the time to leave some time for questions. Maybe I'll just skip those and just highlight some of the problems that we are still facing, and if anybody is interested in working in these areas, so you will have things. So just to summarize, what we have shown is that you started with a concept of, can we apply a computational model to design next generation of AI models? And by following the philosophy of how the brain works, you led to new concepts, both in the modern half-field network lineage and in the episodic memory lineage also, where you have a dependency between semantic and episodic memory. And these are not just theoretical concepts, these are now practical and actually appearing in products, because it's easy to implement them from a neural network standpoint, but those key ideas carry through and have some sound backing from how the brain does as such. But there are many problems. This is still not solved in this space. That's why it's a grand challenge. And what are all these cells doing? What are the grid cells doing? What are the place cells doing? And what are the pyramidal cells doing in the entorhinal cortex as they cross layers to convey information? And if we could model those, would we get some new neural network architectures? So there's quite a few such open problems out there. From a storage perspective, the brain has finite storage, right? And it's able to take information in and flush things out and do selective forgetting in a way that is optimal for you. But in a computer memory systems, we don't have a good way of doing selective forgetting yet. And besides, we don't have a way of containing storage in the sense that as the amount of information to store, it keeps growing now linearly, but now with new techniques, we can go logarithmically perhaps, but still it's not flat as such. So one dream goal of our research project is to get to that stage where we be as efficient as the brain so that as you store more information, you don't explode, you just stay in a stable manner there as such. Yeah, and then there are other problems in terms of how does the entorhinal cortex bring together text and image field to combine together? How does the fusion happen? Is there different algorithms that the brain is using for fusion? So I have another project that deals with multimodal fusion algorithms. So if you track my publications, you'll see a number of neural architectures we've come up in that space, also using the concept of hypergraphs and connecting them in layers as such, so you can follow some of that work as well. Anyway, so this was my pet project currently, and I'm happy to answer any questions you guys may have on this. Yeah, go ahead. The variational autoencoders?
DALI is that.
Oh, DALI.
What kind of model they use?
So DALI is discrete variational autoencoders. So they use a vector quantization scheme to represent, and that quantization gives you the robustness from a separation standpoint. Yeah, even though it is not in an older technique. Of course, there is DALI 2 that has come out and so on. And people are getting better and aiming for that. I mentioned the reconstruction as one of the problems. That is still something that's up for grabs for anyone who wants to work on that area. Any other questions?
Actually, it was a great lecture. We started off with memory prosthetics. Came all the way to how we draw back to how we draw. It was great. We also get an excellent exercise of identifying laws of confidence.
It's already taken, sorry.
You
Yeah.
said you're trying to say it's bio-inspired or neuro-inspired. So it's still like an inspiration, neuro-inspired. But it's not like functional activity-wise, you are trying to get something similar. But maybe the implementation of the brain and this is still not.
Yes. I think that's a very good observation, and I'll tell you the reason for why we took this approach. We had another project called neuromorphic computing. I don't know if you've heard of these. There's North Pole, there's chips now coming out in Samsung and others that are the brain chips, they're called brain chips. And their first experiments were simulating the brain neural networks, and they said, oh, we simulated the cat's brain and so on. So simulating meant interconnecting, but not from a cognition standpoint and the reasoning standpoint. So many of the work that do claim from a neuronal connection perspective, focus on some very narrow things. And so we took the approach that let's use it as inspired, meaning follow the principles that they're doing. And if you go to old definition, probably still the functional definition of artificial intelligence is not do as the humans do, but do as the functions of what the humans do, and in a way that accomplishes the same objective. And if that is close enough to what you're doing, it doesn't have to actually be, uncovering this, the brain's mechanism, because it's too complex for us to still understand that aspect of it. So that's why the neuroscientists took an approach of, I'm going to study one cell at a time. But that field has then not moved fast enough for us, so to be practical for us to put these things together. But having said that, the long-term goal of this project is to learn from these two, go back to the neuroscientists and ask them to verify the information we found. Like this methodology of semantic and episodic memory linkage, can we find evidence for it in the brain? Can actually take cells that are interconnected between the two subsystems, and what information is going through in those? Those would require MRI studies, functional MRI studies. It would also require breaking apart. I mean, the question is also, what systems do you study them in, rats or monkeys and so on, and that's a whole field in itself. But this is how NeurIPS as a conference started, where people got together, neuroscientists, and there is going to be a forum here as well. We are also trying to organize a workshop in this space. But bringing the two field people together to start discussing what to feed, because they've sort of stagnated in their respective domains. And to make further progress, we need to kickstart those discussions again. But that's a good point. Sorry, you were asking a question? Yeah.
Hi, I'm Fahad. So you talked about, so I'm coming from a really novice background. I know about LLMs and the transformer models. So my understanding currently is like there is a sensory part, there is a storage part, or like embedding part and encoding part, and then a retrieving part. And there was an attention part, right, at the top of it. So I was thinking, like, how does the attention part affects all of these three? Because you explained about all these three, like I was able to understand semantic and memory and how they are related. So I was thinking, can the attention can be a really important factor where you can optimize it more?
Yeah, very much so. The attention plays a role in each stage of the processing. If we had focused a bit more on the computational model side, you could see how it's modulating. As an example, the first stage of sensory processing, it is operational to limit the amount of things you see in the first place, for whom the future representations will be created. But because we are doing a saliency map representation in the brain, there are at different levels. There is the abstracted representations that are ultimately going in long-term storage, but there's also half-constructed sensory maps, which are called the saliency maps, that underlie the attention system in the brain. So that when something you ask for, as you observed from a data-driven perspective, what you observed, you process, you go and represent them. But then when somebody asks a question, in that motorcycle image, was it being ridden by a male or a female? How would you answer that? You kind of mentally reconstruct the scene. You don't know how good your reconstruction is, but how did it start? You had a saliency map representation that is created from in the sensory processing. And as I mentioned, the long-term memory is going back to the areas where the respective sensory systems are. So now you have the saliency maps from which it can reprocess to surface up that information. So while the attention is getting it in the first place to see what comes in and then immediately goes in there, but there are some underlying representations still being stored so that you can evoke. And that's another important paradigm in current systems, is continuous learning in certain systems, is how do you uncover more and more information in response to queries. So that will also be the case. Yeah, so that's one example of attention. But we can say in each stage of the processing, attention drives. Now, you may have a question, since you said you worked in language models, what's the relation of that to LLM's attention model? I have to admit that to me, that was the biggest disappointment in learning about transformers when I heard the term attention and how it was being used and how I developed it during my attentional work. It was a big change for us, because that's more a pay attention type of selection, not an attract attention. The whole goal of attract attention is you don't have to do the detailed processing before you select. It has to pop out. Whereas in a transformer model, you're actually correlating every pair of words from across and doing this in levels of architecture before you do a winner select of some kind. And that's too long a process. And that's not how the attract attention mode works. So if I were doing it, that's not how I would do it. Yeah. Any other questions? Yeah.
People are talking about AGI now.
Yeah.
So will it lead to the realization of AGI?
Yeah, I mean, AGI is one big component of that is reasoning. So, and it turns out that memory and reasoning are two big topics in AI now. And but most people who learn about memory in AI are using it as a way to store temporary information in a neural network. I mentioned that use case in the beginning itself, memory networks. When you think about memory networks, they're actually a place to store your data so you can retrieve it. but it's not actually trying to model, hey, how does the hippocampal actually represent that information? It's like a parking place for them. But that reasoning, so to do AGI, you need both. Memory would be one of them, but most people are only focusing on reasoning now. And to me, that's a gap. Yeah. Yeah, I have some opinions on benchmarks too. I mean, a lot of, and this is not to criticize anybody, but the name of the game in building AI models, we in IBM do too, the Granite models and all, and there are leaderboards out there which people have come up with, question answer situations, for example. Here's a question, here's an answer, and we think that's a good answer. And I was like, how did you evaluate that? Because coming from a clinical background, from the work that we've done in the past, if you think of like say a automated report generation for chest x-rays, that's one of the examples where we use Gen AI, right? We have now a concrete way to measure the accuracy of it, right? Because there's evidence in the image, and then the stuff that you're saying, the clinician can validate for you. But in the context of Gen AI benchmarks, that is not the case. The way they are measuring accuracy is using, metrics that are not tied back to that kind of concreteness for evaluation. For example, perplexity scores or blue score-based matching. Those sort of lexical matching or semantic matching, when the semantic representation themselves are incomplete, as you just saw here. So the benchmarks evaluation and doing good on the benchmarks is an artificial way of saying you're doing good, and that's why having AI work in enterprise systems has become a big problem now, because all these models do well on these benchmarks, and then when you put them to use in enterprise applications, they don't answer. I mean, it's very hard to get them to answer the right way. And that's because they lack the domain knowledge, for one thing, because with the way they have learned across the board, but also the methodology itself. If you look at the chat methodology, it's basically conditional dependency generation. How much knowledge can you convey through that? So I think both the evaluation benchmarks are a problem, and the entire generative AI methodology is a problem with just using conditional dependency generation. We need newer models to emerge in those spaces as well. What do you mean computational? I mean, the search that is happening in the Beam search is computational within a language model as a generative AI. I see. Of course, getting the domain knowledge into the machine itself is a problem. If you don't have in exact forms of expressing it. Okay, any others?
Most of your model you said is about database architectures and computational-wise database architectures and most of the matrix kind of computations, right? Do you think other kind of computation which are coming into, like you said, neuromorphing, spiking, those kind of hardware architectures will be able to optimize these kind of, brain modulated functionalities?
Yeah, I mean, I think the spiking neural networks has been around for some time. None of these are like new in the sense that the concept of spiking neural networks has been around, but it was hard to get them to realize at the same scale as artificial neural networks with GPUs and other architectures coming in. So there's still some potential for those, but again, there is political lobbying going on in the communities. The communities that support the artificial neural networks will try to prove the others as not being scalable, and there isn't enough momentum in the spiking neural. But there's a small community. I do interact with this. Even in IBM, we have groups that work in spiking neural networks. It has potential, but each is limited by some way. So I think the hardware limitation that was there for artificial neural networks has gone away, but not so much for spiking yet. When that happens, you might see that field take off even more. Any other? Okay, I think I might be running short on time. Thanks, guys. Thank you for all. Thanks for your attention.
Thank you, ma'am. Our deepest gratitude for the enlightening lecture you have shared with us today. Your passion has undoubtedly inspired us all. In a way of expressing profound admiration and gratitude, ladies and gentlemen, let us take a moment to honor the speaker of today's event. I now request Professor D. Ramakrishna Sir, Head Department of ECE, to perform the honors to Dr. Tanvi Saida Mahmood ma'am. I also request Professor S. Ramchandram Sir, former Vice Chancellor Usmania University, and Professor Samin Fatima ma'am, former Principal University College of Engineering Usmania University, and Dr. D. Vijay Kumar Sir, President OU Alumni Association, to please join for the felicitation. Also Kishore Kumar Sir, President ECE Alumni Association, to please join for the felicitation. Ma'am, you want to have some water? All the faculty members of ECE department and the family members of Professor Alladi Prabhakar sir to join for the felicitation. I request Naveen Kumar sir and Rajendra Naik sir to join. I request Lakshman Rao sir also to join. I request Sudha ma'am also please join the felicitation.
Celebrate comfort versus. Come on, sir. Koncham.
Okay, ready, sir?
One second. Thank you, sir.
Now I would request Dr. M. Shamsundar sir, Associate Professor, Department of ECE, to present vote of thanks.
So, good evening to distinguished guests. I take the honor to propose a formal vote of thanks to all the dignitaries who have made it convenient to attend this Professor Alladi Prabhakar 6th Endowment Lecture organized by the Department of Electronics and Communication Engineering, Usmania University. It is with immense pleasure and gratitude that I extend my heartfelt thanks to our distinguished speaker, Dr. Tanvi Saida Mahmood, for gracing us with her presence and delivering an enlightening and thoughtful provoking lecture today. We are truly honored to have an opportunity to benefit from Dr. Tanveer Saida Mahmood with her wealth of knowledge and expertise in the topic Neuro-Inspired Memories, driving next-generation AI models for the computer systems. The insights shared today have not only broadened our understanding but have also left a lasting impact on our perspective. I would also like to extend our thanks to Honorable Vice Chancellor Professor Kumar Sir, Osmania University, former Vice Chancellor Professor Ramchandran Sir, Osmania University, former Principal Professor Sameen Fatima Madam, Principal College of Engineering, Dr. D. Vijay Kumar, President of Alumni Association OUCE, Shri P. Kishore, President of EC Alumni Association, Professor P. Chandrasekhar Sir, Principal UCOU, Professor D. Ramakrishna, Head EC Department, who has been instrumental in making this event successful. Our special thanks to the family members of Professor Alladi Prabhakar and all the retired professors of our department for taking the time to attend the lecture. As we conclude this event, let us carry forward the inspiration and guidance we have received from our dignitaries. Their contribution today will undoubtedly shape our future endeavors. Sincere appreciation to all my colleagues, teaching staff, non-teaching staff, and student coordinators for making this event possible. Thank you to all the attendees for your active participation and enthusiasm. Thank you one and all. I request all to stand for a national anthem.
अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्तर बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय